As usual, we start designing our dynamic programming algorithm by defining a subproblem in a way that allows us to solve a subproblem by solving smaller subproblem. As we said already, this is probably the most important step in designing dynamic programming solutions. So before doing this, we define our problem formally. So the input consists of n digits, d1, d2, and so on, dn, and then -1 operations between them, which we call op1, op2, and so on, opn. Each operation is either summation, subtraction, or multiplication. And our goal is to find an order of applying these operations so that the value of the resulting expression is maximized. As we discussed already, we can specify this order just by placing parentheses into our expression. We start building our intuition by reconsidering our toy example. So assume that the multiplication is the last operation in some optimal ordering, in an ordering leading to an optimal value in this toy example. Well, this means that in this expression we already have two pairs of parentheses, and our goal is to parenthesize the initial sub-expression and the second sub-expression so as to maximize the value. This means that it would be good for us to know what is an optimal value for the first sub-expression and for the second sub-expression, right? And in general, if you have an expression and if you select an arithmetic operation, which is the last one, then it splits your initial expression into two sub-expressions, right? And for both of them, it would be good to know an optimal value. And in turn, each of these two sub-expressions are split into two sub-expressions by the last arithmetic operations, and so on. So this suggests that a good subproblem in our case would be to find an optimal value for any sub-expression of our initial expression. So we've just realized that it would be good to know the optimal values for all sub-expressions of our initial expression. What do we mean, however, by saying optimal values for all sub-expressions? Assume, for example, that we need to compute the maximal value for the sum of two sub-expressions, sub-expression 1 and sub-expression 2. Well, this obviously means that we would like this sub-expression to be as large as possible and this sub-expression to be as large as possible. If, on the other hand, we would like to compute the maximal value of sub-expression 1 minus sub-expression 2, well, this means that we would like sub-expression 1 to be as large as possible, while we would like the value of sub-expression 2 to be as small as possible, right? Just because we compute sub-expression 1 minus sub-expression 2. This suggests that knowing just the maximal value for each sub-expression would not be enough. And this usually happens when designing a dynamic programming solution. This also suggests that instead of computing just maximal value, we will maintain both the maximum value and the minimum possible value for each sub-expression. Let's illustrate this reasoning once again on our previous toy example. So in this case, we are maximizing the product of two small sub-expressions. In this case, these two sub-expressions are so small that it is not difficult to compute their minimal and maximal values. For example, for sub-expression 5 minus 8 plus 7, the minimum value is minus 10 and the maximal value is 4, right? At the same time, for the second sub-expression 4 minus 8 plus 9, the minimum value is minus 13, while the maximum value is 5. Right? Now we would like to parenthesize both sub-expressions so that their product is maximal. Well, it is not difficult to see that in this case the optimal way to do this is to take the minimal values of both sub-expressions. Right? So this will give us minus 10 multiplied by minus 13, which is equal to 130, right? Which is much larger than the product of the maximal values of these two sub-expressions, which is 4 by 5, which is 20 in turn. Okay, we are now ready to write down the recurrent relation for our subproblems. Before this, let's formally define E of ij to be the sub-expression of our initial expression, resulting by taking digits from I to j and all operations between them. Then our goal is to compute the maximum value of this sub-expression, which we denote by capital M of ij, and the minimum value of this sub-expression, denoted by M of ij. Okay, consider our initial sub-expression from I to j, and assume that we would like to compute one of the extreme values of this sub-expression. I mean, either the minimum or the maximum. Well, we know that in any ordering for this sub-expression, there is some last operation, say OPK. So this operation splits our initial sub-expression into two sub-expressions. Namely sub-expression ik and sub-expression k plus 1j, right? So to compute the maximum value, we just go through all possible such case from I to j minus 1 and through all possible extreme values for two sub-expressions. I mean, either we apply operation k to the maximum values of these two sub-expressions, or we apply operation k to minimum values of these two sub-expressions, or we apply it to the maximum value of one sub-expression and the minimum value of another, or vice versa, right? To compute the maximum value of sub-expression ij, we just select the maximum among all these possibilities, while to compute its minimum value, we simply select the minimum among all such possibilities.